Hello, I am MD Rakibul Hassan, presenting our paper Diagnosing Autism Spectrum Disorder using Ensemble 3D CNN, a preliminary study in IEEE International Conference on Image Processing. So these are the outlines of my today's presentation. First, I will be talking about background and specific problem statement that we wanted to solve, and what could be the prospective solutions, and what are the different literatures, that means what is already known to us. And as this is a works involving deep learning methods, of course, we'll be talking about the data set, the architecture, the hyperparameter settings, and also the other algorithms that we use to compare our 3D CNN models performance. And then we'll be talking about the results, and we'll be discussing our results, followed by comparative analysis with already published works. And then I will be summarizing our works with possible future work direction and the references used in our articles. Now, let's talk about autism spectrum disorder. So what is ASD? It is a neurodevelopment disorder, and that basically affects children's cognition capabilities and motor skills. So it affects 1 in 160 children over the world, according to World Health Organizations, and it mostly appears in early childhood. So that's why early diagnosis is important. Whereas traditional diagnosis methods often lack objectivity, and also it has a higher rate of misdiagnosis. In traditional method, doctors usually assess patients' behavior. So this is kind of subjective. So that's why what could be the prospective solution? So we can use deep learning because deep learning has been used in so many medical diagnosis methods nowadays. So we can use deep learning to diagnose ASD. For data to train the deep learning models, we can have functional magnetic resonance imaging of the brain, and there are different deep learning models available. We'll be specifically talking about convolutional neural networks, and with the data and the models, we'll be having the SD diagnosis. We'll be having the performance in terms of accuracy, sensitivity, specificity, and also it is also possible with other scores as well. Now, let's talk about some already published works. So several works should prove a concept of using deep learning in ASD. For example, a reference 4 used CRADEC 200 Atlas in extra trace and support vector machine algorithm. Now, what is Atlas? So Atlas is basically boundaries of different region of interest in our brain, which helps us to understand and interpret. So the reference 9 used a multi-atlas, that means they used multiple atlas with ensemble learning. Reference 10 and 11 used Harvard Oxford Atlas, whereas 10 used a graph convolutional network and 11 used a convolutional neural network ensemble model. So we can see that different researchers used a range of atlases and also a range of deep learning models. So let's talk about the data set. Autism Brain Imaging Data Exchange 1, which is a very well-known database used in ASD diagnosis in different works. So it is basically resting state fMRI images of more than 100 individuals, where 539 was ASD patients and 573 was healthy controls. Now, it was collected from 17 different geolocations. Those are basically different institutions across the world. And the data was manually inspected by neurology experts. So that means the data is quite authentic to use in ASD diagnosis methods. Now for the pre-processing portion, so several pre-processed AVID1 dataset is already released by pre-processed Connectome project. Among them, we used a configurable pipeline for the analysis of Connectome pipeline. This is also a well-known pipeline used by many researchers. So we'll be noticing this when we'll be comparing our works with other researchers. Now, to remove the fMRI artifacts resulted from different physiological or mechanical issues, we applied a bandpass filter of 0.01 to 0.1 Hz, and that resulted as 860 RS fMRI. Among them, we have 440 ASD individuals and 420 healthy controls. The data from these particular ASD individuals and healthy controls we basically used in our model. Now, regarding the atlas selection, so reference 11 and 4 showed CRADOC 200 and 400 atlas are more suitable for ASD prediction, whereas reference 13 showed automated anatomical labeling, that is AL116 atlas performed better in ASD prediction. So we applied all three atlases, both on individual level and also combination of all three atlas together. Now, this is the particular architecture of 3D CNN model that we use. So this is the RS fMRI images from both ASD patients and healthy controls. And as we mentioned that we have three atlases. So for three atlases, we have three different brain parcellations or brain regions. We calculated functional connectivity matrices for all three atlases. And then we applied three distinct CNN models on three different atlases. So these three CNN models are distinct, they're different from one another. So of course they will provide the SD diagnosis scores separately, and then as an ensemble approach, we provide the final prediction. So let's talk about the three distinct CNN models. So this particular figure demonstrates us the three CNN models. Now, if we look into here, so these are the input 3D functional connectivity matrices. Now, first of all, we have average pooling and followed by different convolutional layers and exponential linear unit activation function. And also we have the max pooling followed by flattening and dense layer. As we know that after convolutional layer, after flattening those data, we will be having a dense layer. So we have used two dense layer, one having 16 neurons, and finally we have a one neuron final output layer, because this is a binary classification problem. And also in the dense layer, we have used ELU activation function. And these are different filter size that is being used in different convolution layers. And if we look here, so they are different from each other. And specifically regarding the number of convolutional layers, so we can see that for CC400 Atlas CNN, we used an additional convolutional layers having 64 filter size. Now, these are the hyperparameter settings. So we used binary cross entropy as loss function. We used mini-batch training with 64 batch size. And for optimizer, we use stochastic gradient descent with the following learning rate and momentum. We trained each parcellation for 50 epochs, and we noticed that there was an overfitting issue. So we used L2 regularization with 0.005 as the parameter value. And also we applied dropout of 0.5 value, and specifically for dropout for AAL116 CNN, we applied one special dropout between the convolutional layers. And whereas for CC200 and CC400 CNNs, we applied uh, one additional one dropout between the two dense layers. And regarding this hyperparameter setting, so we also tested with other hyperparameters, and we found that this particular setting is best for our configuration. Now, to compare our 3D CNN model's performance, we also implemented support vector machine algorithm with sigmoid kernel, and also random forest algorithm with SQRT max features and balanced class weight. Now, to evaluate the model performance, we used accuracy, specificity, sensitivity, and area under the receiver operating characteristics graph. And specifically, we used five-fold cross-validation. So while 860 subjects were divided into 5 subjects, one particular subject was the testing set, and other 4 subjects were training sets. And we iterated the process for all 4 subsets. So we got 5 different test accuracy. The mean accuracy and also the standard deviations are reported. For example, this particular table 1 is reporting the 5-fold cross-validated results of CNN models. So first of all, we applied 3 different atlases performance. This is being shown here, and then the combined ensemble approach performance is shown here. Now, if we look here, so the combined approach consistently performed better for all 3 scores like accuracy, sensitivity, specificity. So we can say that we achieved 74.53% accuracy with the ensemble model. We also calculated the area under receiver operating characteristics curve, which appeared 0.74 for the ensemble 3D CNN model. Now, as we mentioned that we used SVM and RF to compare the performances. So these are the performances using SVM and RF machine learning model. So we found that the accuracy was roughly the highest accuracy here using CC200 Atlas is 71.48%, whereas using Ensemble 3D CNN we found around 74.53%. So of course, the Ensemble 3D CNN model performed better as compared to SVM and RF. Now, we further observed that the accuracy fluctuates significantly during training. So, we found that the test accuracy decreased remarkably for particular specific data set. So, we discarded those particular data set. So, we had then 554 subject, and using those only 554 subject, we found that the mean accuracy increased to around 80%. So, previously it was 74.53%, then it was 80%. So of course around more than 5% increase. So of course we can say these are the outliers, and also we take the data and we found that these data are either too small or too large as compared to other data. So these are the outliers, and if we remove the outliers we can achieve, let's say, 80% accuracy, and we found that 80% accuracy using the ensemble 3D CNN model. Now, if we compare our works with the already published works, so we found that those works that use about one data set, and there's a different pre-processing method. Remember, I mentioned that CPSC pipeline has been used mostly in different literature, so we can find the proof here. So there are different algorithms used by different researchers, and now if we look into the accuracy, so our accuracy outperforms all study based on the full scale about one data set. Now, one particular study here, reference 5, they showed around 90.39% accuracy, but they used only the subset of the about one dataset having the size of only 182. And remember, we used around 860 individuals dataset, and we used the full scale dataset, whereas this particular reference used only a subset from one particular source, whereas we used dataset from all 17 geolocations of the ASD abide one dataset. So of course this justified their higher accuracy because they used only a subsection of the dataset. And we also showed that if we just remove the outliers, then we can have around 80% accuracy. So of course if we remove the other dataset as well, so we can have more accuracy there. Now to conclude, so of course we provide a detailed analysis of applying 3 suitable CNN models for 3 different atlases on RS ephemeral data. So first of all, we calculated 3 functional connectivity matrices based on 3 different atlases. Then for 3 different atlases, we applied 3 distinct CNN results. So this is different from previously published result. Previous published result either used a single CNN models for different atlases during their ensemble model, or either they used a single atlases, whereas we use different atlases, and for different atlases we use different CNN models, and that's why we believe that we achieved higher accuracy than others. So we achieved 74.53% accuracy, that is outperforming state of the our result on ASD diagnosis who used full scale abide one dataset. And for future work, so we can extend our method to more atlases to check its robustness and applicability. We can use the Harvard Oxford Atlas, for example, and we can evaluate different combination of atlases and deep learning models. So of course, we have other choices of deep learning models like say graph convolutional networks or attention models and so on. So that would provide us a robust and trustworthy ASD diagnosis and prognosis system. And also, as we found that several geolocations data has either has outliers, so what if we can apply more rules and disciplines while selecting the data? So if we apply more rules and disciplines among site, age, and sex dimensions while selecting the data, we believe we can have a more robust and trustworthy ASD diagnosis model. And these are the references that we used in our article. So thank you for your time for hearing me. So that's all from me. Floor is now open for discussion.